James Webb deepened crisis in cosmology. For more than a half-century, scientists have been developing a remarkable account of how the universe evolved. Initially called the Big Bang, this account was refined as time went on, until it came to be known as the Standard Model of Cosmology, Inflationary Cosmology, or the Lambda CDM model. What these various names underscore is that the story of cosmic evolution, told by physicists and astrophysicists, includes various phases, like inflation, and various actors, such as dark energy and dark matter. While the Standard Model is rich in successful confrontations with observations, cracks have appeared in its foundations over time. And it's getting worse when the addition of humanity's greatest space-based observatory of all time, the James Webb Space Telescope, revealed our universe in a whole new light, with unprecedented resolution and wavelength coverage to view the cosmos. In recent years, many have been claiming that there's a crisis in cosmology, and that in particular, a series of James Webb observations, including the fact that different methods of measuring the expansion rate yield different results, that big, bright, evolved galaxies appear seemingly too early, and that predictions from dark matter simulations don't match the internal motions of stars within galaxies, all point to a coming and necessary scientific revolution.
That's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden we realize that we may have to rewrite all the textbooks about the beginning of the universe.
Join us as we dig deep into how James Webb just shattered our cosmology. The cracks in cosmology. The cracks in cosmology. Cosmology is the ultimate science. It deals with the birth, evolution, and fate of the universe. The Standard Model consists of several ingredients: the Big Bang, dark matter, dark energy, and inflation. First, take the Big Bang. Astronomers can see that the galaxies, the basic building blocks of the universe of which the Milky Way is one, are flying away from each other in the aftermath of a titanic explosion. They also observe that the universe is permeated by relic heat, the cosmic background radiation. Together, these two observations tell astronomers that the universe was smaller and hotter in the past. In fact, according to the standard picture, the universe was born in a blisteringly hot fireball 13.82 billion years ago and has been expanding ever since, with the galaxies congealing out of the cooling debris. But the basic Big Bang picture requires a few extra ingredients because it conflicts with observations. First, and most seriously, it predicts that we should not exist. According to the basic Big Bang, when matter emerged from the primordial fireball, it was spread extremely smoothly. Thereafter, regions that were slightly denser than average pulled in matter faster with their stronger gravity. The result of this process, akin to the rich getting ever richer, were the galaxies we see today. The problem is, it would have taken longer than 13.82 billion years to assemble galaxies as massive as our Milky Way. Cosmologists fix the problem by bolting invisible dark matter onto the basic Big Bang. Invisible dark matter outweighs the visible stars and galaxies by a factor of 6, and its extra gravity speeded up galaxy formation. The second way in which the basic Big Bang picture conflicts with observations is that it predicts that cosmic expansion should be slowing down. Gravity acts like a web of elastic between the galaxies, breaking their rush from each other. But in 1998, astronomers discovered that, contrary to all expectations, the expansion is speeding up. They fix this by bolting dark energy onto the basic Big Bang, something that's invisible, fills all of space, and has repulsive gravity. It's dark energy that's speeding up cosmic expansion. The third way in which the Big Bang picture conflicts with observations is that universe has the same temperature everywhere, the temperature of the cosmic background radiation. That temperature is 2.726 K. Absolute zero is K. Early on in the Big Bang, regions that are today on opposite sides of the sky were too far apart to equalize their temperatures. Cosmologists fix this by postulating that, early on, the universe was far smaller than expected. It must therefore have expanded faster to achieve its current size in 13.82 billion years. In fact, the universe, in its first split second, is believed to have undergone an expansion so violent that it's been likened to the explosion of an H-bomb. This is compared with the stick of dynamite of the Big Bang expansion, which took over when the initial inflation ran out of steam. There you have it. The standard model of cosmology equals the Big Bang plus inflation plus dark matter plus dark energy. Technically, it goes by the name of lambda CDM. Whereas the Big Bang and inflation is implicitly assumed, lambda is shorthand for dark energy and CDM for cold dark matter, with the cold meaning that its components move sluggishly so gravity can concentrate them into clumps. Something's wrong with cold dark matter. The first way lambda CDM conflicts with observations involves clusters of galaxies. According to the cold dark matter model, gravity will cause dark matter to clump on a range of scales, including those smaller than a galaxy cluster. Later, ordinary matter, which forms into stars, is pulled in. These subhalos may have plenty of stars, but some subhalos may have no stars, or so few stars that they're invisible. There is a way to reveal them, however. A team led by Dr. Massimo Meneghetti of the National Astrophysics Institute in Bologna, Italy, observed 11 galaxy clusters with the Hubble Space Telescope and the European Southern Observatory's Very Large Telescope in Chile. They examined the light of more distant galaxies and how it was distorted or gravitationally lensed due to passing by the invisible subhalos. To the team's surprise, the lensing by subhalos was much stronger than expected, indicating that they're very compact. This conflicts with the cold dark matter model, which maintains the subhalos should be much puffier. We need to know if this anomaly can be caused by the way we analyze our data or the way we make our theoretical predictions. If we fail to explain it, the only option will be to revise the model. One possibility is that the dark matter isn't made of what we think it's made from. Favored candidates are massive, weakly interacting particles that interact with ordinary matter only through gravity. Such weakly interacting massive particles, or WIMPs, aren't part of the standard model of particle physics, but are predicted by a speculative theory called supersymmetry. Possible alternatives include a new type of neutrino called a sterile neutrino, another class of particles called axions, or even primordial black holes, formed just after the Big Bang. The smoothness of matter. The second conflict between lambda CDM and observations concerns the clumpiness of matter on a large scale. A team led by Prof. Koen Kuijken at the Leiden Observatory in the Netherlands looked at the distribution of 31 million extremely faint galaxies in the latest data release of the European Kilodegree Survey, KIDS. The KIDS collaboration used the Very Large Telescope's Survey Telescope in Chile to observe two large swaths of sky. Specifically, Kuijken's team looked at how the light of these galaxies was gravitationally lensed by the matter between them and Earth, enabling its distribution. It discovered that matter was spread 8.3% smoother than predicted by the cold dark matter model, which takes the very small variations in the density of the universe shortly after the Big Bang, revealed by the cosmic background radiation, and calculates how these would have been enhanced by gravity over the past 13.8 billion years. Once again, the anomaly might go away with a better analysis of the data or a modification of the cold dark matter model, or it could be telling us the model is fundamentally wrong. Measuring the Hubble constant. The third conflict between lambda CDM and observations, known as the Hubble tension, concerns the Hubble constant, a measure of the current expansion rate of the universe. There are two ways to measure it, and they're contradicting each other. One way is to look at subtle variations in the temperature of the cosmic background radiation across the sky. These were imprinted on the radiation by the fluid of matter and radiation at the beginning of time, as it sloshed about like water in a universe-sized bath. It's possible to extract from these sloshing modes all the key cosmological parameters. The European Planck satellite, for instance, found that the universe is 5% atomic matter, 27% dark matter, and 68% dark energy. Crucially, such observations also reveal the Hubble constant in the early universe, and this can be extrapolated to the present time. And herein lies the problem. The extrapolated value is about 10% smaller than the Hubble constant observed today. A key thing to bear in mind is that the Hubble constant deduced from the cosmic background radiation is very precise because the physics is simple and well understood. But measurements of the Hubble constant in today's universe are cruder and fraught with problems. Such measurements involve finding objects that are believed to always have the same intrinsic luminosity, such as Cepheid variables and Type 1a supernovae. Like standard 100W light bulbs strung across a field at midnight, such standard candles reveal their relative distance by their relative faintness. The trouble is that the physics of such stars is not well understood and may not be as standard as we hope. So, it could be that these measurements of the distance of standard candles as they're dragged away from us by cosmic expansion are in error and will eventually yield a Hubble constant in line with that from the cosmic background radiation. James Webb has discovered the absolutely impossible. But when James Webb, the largest, most powerful, and most complex telescope ever launched into space, began its journey to conquer the universe, it deepened the cracks in cosmology. To start, it's helpful to recall what James Webb was built for. On Earth, astronomers often build telescopes on mountaintops and in remote deserts for an unobstructed view of the sky. But the Earth's atmosphere still mars the view. Space, as NASA explains, is the ultimate mountaintop. James Webb launched in December 2021 as the successor to the Hubble Space Telescope, and it improves on its predecessor in several ways. For instance, because of its huge golden mirrors and infrared cameras, it can make better observations of planets orbiting stars other than our Sun. But for this discussion, what matters is how it can observe farther back in time than the Hubble telescope. In astronomy, the farther away an object is in a telescope's mirror, the older it is, because light needs time to traverse such large distances. Some of the light Webb captures is almost as old as the universe itself, dating back to 100 million to 250 million years after the Big Bang, the relatively infant days of our universe, which is believed to be 13.77 billion years old. That light is so far away, it has been traveling nearly the age of the universe to reach us. So, when the telescope focuses its mirrors on a particular patch of sky, it can see through time. The farthest objects in the image are the oldest. Those in the foreground are more current. The images that contain this rich history are called deep field observations. And while they appear in two dimensions to us, in them, scientists can see how the universe has evolved. Before James Webb, the Hubble Space Telescope gave humanity its deepest look into the evolution of space. And in the Hubble images, scientists saw a pattern. As they peered farther back in time, there were fewer and fewer galaxies, and they were smaller and smaller. This makes intuitive sense. Just like fossils in the oldest layers of the Earth's crust represent more primitive forms of life, the oldest galaxies in a deep field image ought to represent more primitive galaxies. And they differ from modern galaxies because they had the shortest amount of time to assemble. They were like teenagers compared to the large adult galaxies of today. When James Webb went online, astronomers were eager to peer a bit more deeply into the past. They thought the pattern from the Hubble images would just continue. But that's not what they saw. The trouble began almost as soon as James Webb first peered into the distant universe. Its first views of such distant, ancient regions of space were confusing in two ways. First, some of its images contained huge numbers of galaxies, far more, in fact, than astronomers thought possible so far back in time. Second, a handful of those galaxies appeared to be monstrously massive. These all dated back to the first 700 million years of the universe, and they were up to 100 times as heavy as scientists thought possible back then. For that reason, these galaxies were dubbed universe breakers. Our current understanding of how the universe grew up goes like this. First, dark matter collapsed into giant clumps known as halos. This happened within the first few hundred million years after the Big Bang. The halo's gravity then pulled in normal matter. This eventually formed stars and galaxies. This would have taken time. Matter would have clumped together slowly, eventually building up larger and larger galaxies. If true, the jumbo galaxies that James Webb spied so soon after the Big Bang shouldn't be possible. What's more, the current story of the universe doesn't predict nearly enough dark matter halos in the early universe as would be needed to build the many big galaxies that James Webb saw. In that light, things look pretty dire for scientists' current theory of how the universe evolved, which makes scientists think they are missing something in their understanding of the universe, something potentially very big. This has raised some concerns that the history of the early universe needs to be rewritten. But despite these gaps in knowledge, it is actually human nature, our tendency to interpret data to fit our beliefs. That is the biggest threat to modern cosmology. In cognitive science, confirmation bias is the effect where people tend to unconsciously interpret information in a manner that leads to a selection of data that confirms their current beliefs. For cosmologists, this means the unconscious or conscious tuning of results, such that the final cosmological interpretation tends to confirm what they already believe. This is particularly pernicious in cosmology because, unlike laboratory-based experiments, we cannot rerun our experiment many times to investigate statistical anomalies. We only have one universe. A study that surveyed all the published cosmological literature between the years 1996 and 2008 showed that the statistics of the results were too good to be true. In fact, the statistical spread of the results was not consistent with what would be expected mathematically, which means cosmologists were in agreement with each other, but to a worrying degree. This meant that either results were being tuned somehow to reflect the status quo, or that there may be some selection effect, where only those papers that agreed with the status quo were being accepted by journals. Unfortunately, the problem is only going to get more difficult to avoid as experiments get better. Ask most cosmologists what they think dark energy will be, and you will grudgingly receive the answer that it is probably a vacuum energy. Ask most cosmologists if they think Einstein's theory is correct on cosmic scales, and you will grudgingly receive the answer that yes, it probably is correct. If these assertions turn out to be true, how can we convince the wider scientific community and humanity that any cosmological finding is not just the result of getting the answer we expected to get? There are 3 solutions to this problem that are equally important. Blind analysis is the most straightforward and obvious thing to do, and has also been the most talked about. In this case, the aim is to create data sets that have randomized or fake signals in them, where the scientists doing the cosmological analysis are blind, meaning do not know if they are working on the true data or the fake one. Blind analysis and control samples are commonly and successfully used in biology, for example. The problem in cosmology is that we have no control group, no control universe, just one. So any blind data has to be faked or randomized. Blind analysis has started to be used in cosmology, but it is not the end of the story. In addition to blind analysis, there are 2 further approaches that are less widely practiced, but no less important. The first is a systems engineering approach to experiment design. In this approach, each tiny aspect of an experiment has a list of demands or requirements and result-independent tests that it must pass before it is used. The idea is that if each subsection of an analysis passes these tests, then the entirety should produce unbiased results. The second is transparency. by publishing data and codes in an open way for anyone to download, then there is no place to hide tuned parameters and dodgy data. By using these three approaches, blinding, systems engineering, and transparency, the next generation of cosmology experiments should be able to convince people that confirmation bias is not a factor in understanding the cosmos. Without them, by looking to the heavens, the most interesting thing we may find is ourselves. Back to James Webb. It could be said that Webb's new look at old data from the Hubble Space Telescope tells another story. James Webb is giving us a new language to understand early universe. But instead of saying James Webb is upending cosmology, we prefer to believe that the telescope is giving us a new language to understand the early universe. In other words, instead of denying Webb's impossible observations, we should understand this language. Either way, cosmology is one part recipe, one part narrative for the creation of the universe as we see it today. Scientists can take the earliest possible observation of the afterglow of the Big Bang, which represents a universe before stars existed. They take that image and, using what they know about the properties of the universe, tell the story of how the universe came to look like it does today. Scientists know the story is incomplete. Huge portions of it, like dark matter and dark energy as told, are still not fully understood. But maybe this story is also incomplete in ways they had not previously considered. And the new James Webb observations could be resolved by tweaking the cosmological model. Some of the tweaks could end up changing the estimate of how old the universe is. Or it could be that dark matter and dark energy are more complicated than scientists previously understood. Or there is some other component of the universe that we haven't even accounted for that's out there. All of those options are disruptive in some way. Of course, it's going to take a lot more careful observations of these galaxies to narrow down the possibilities and figure out why they are so bonkers. And the good news is, there will be time to do it. James Webb is expected to remain online for up to 20 years. That means answers won't come quickly or easily, but to the scientists searching for them, they are simply tantalizing. It's the pure thrill of exploration. As Rohan Naidu, an MIT physicist, said, "Imagine, right, the wonder of the first person who set foot on Antarctica and saw penguins there. That's kind of like the vibe that is happening right now. We're just at the beginning of observing this era of time, which, again, was previously obscured to us." As Irini Lambrides, an astrophysicist working on a NASA fellowship, concluded, it took thousands of people to get James Webb launched. So, it's understandable that it's going to take thousands of people to understand the data that came off of it. We've got a ways to go. James Webb's new discoveries. According to new observations from the James Webb Space Telescope, surprisingly low reservoir of methane may explain how a planet around a nearby star grew weirdly puffy. The finding shows that planetary atmospheres can inflate to remarkable amounts without employing esoteric theories of planet formation, astronomers say. As Michael Line, an extrasolar planetologist at Arizona State University, said in a statement, "The Webb data tells us that planets like WASP 107b didn't have to form in some odd way, with a super small core and a huge gassy envelope. Instead, we can take something more like Neptune, with a lot of rock and not as much gas, just dial up the temperature and poof it up to look the way it does." Discovered in 2017 by the Wide-Angle Search for Planets, or WASP Consortium, WASP 107b, located roughly 200 light-years from Earth in the constellation Virgo, is among the lightest of the more than 5,000 exoplanets found thus far. Despite being nearly as large as Jupiter, WASP 107b weighs just 12% of the gas giant's mass, equivalent to only 30 Earths. For context, one Jupiter mass is equal to about 318 Earth masses. This planet is so puffy, the team says, that its density can be likened to a microwaved marshmallow. From previous observations of WASP 107b's size, mass, and age, astronomers suspected the planet had a small, rocky core enveloped by a rich reservoir of hydrogen and helium gases. However, such a scenario failed to fully explain the remarkably bloated orb, which, despite the fact it orbits its star at 1/7, the distance between Mercury and our Sun, doesn't receive enough energy from its star to account for its cotton-like density. Alternatively, if the planet's core actually held more mass than expected, scientists say the atmosphere would have shrunk as the planet cooled over time, meaning it would have turned out smaller than what is observed. Now, using Webb's data, combined with previous observations from the Hubble Space Telescope, two independent teams of astronomers may have solved the puzzle. In short, they discovered that methane in the planet's atmosphere is 1/1000th of what would be expected for this world. Because methane is unstable at high temperatures, astronomers say the surprisingly low amount is evidence that the gas from deep within the planet is mixing vigorously with cooler layers higher up. And the fact that we detected so little, even though we did detect other carbon-bearing molecules, tells us that the interior of the planet must be significantly hotter than we thought. The extra heat likely comes from the fact that WASP 107b zips around its star every 5.7 days in an orbit that is not a perfect circle, the researchers say. The star's constant gravitational pull on WASP 107b, whose distance from its star keeps varying throughout, stretches and contracts the planet's profile, thereby heating it up. On Earth, a similar force by the Moon causes high and low tides. The planet's hot core, combined with tidal heating from its star, is also changing the chemistry of the gases deep within the planet. As Zafar Rustamkulov, who is a co-author of one of the two new studies, said in a statement, "We think this heat is causing the chemistry of the gases to change, specifically destroying methane and making elevated amounts of carbon dioxide and carbon monoxide." In 2020, a team of astronomers, including Singh, detected helium in the atmosphere of WASP 107b, marking the discovery as the first time this gas was spotted on an exoplanet. The element, which was tentatively spotted on the world in 2018, before having its existence there confirmed 2 years later, was seen extending far out into space as a tenuous cloud. Because this planet's atmosphere so far flung, astronomers say ultraviolet radiation from WASP 107b's star is slowly stripping the world of its air, about 0.1% to 4% of atmospheric mass every billion years, to be more specific, which results in a comet-like tail trailing behind the orb. Thanks to the planet's supremely puffy nature, astronomers can look about 50 times deeper into its atmosphere than they can for a world like Jupiter. Last year, for instance, James Webb observations of WASP 107b's atmosphere showed it rains sand on the planet. In a previous discovery, scientists using the Webb telescope have mapped the weather on a planet 280 light-years from Earth, a hot gas giant with one side permanently facing its sun and the other cloaked in eternal night. The Janus-faced planet, named WASP 43b, is composed primarily of hydrogen and helium, and is significantly hotter than any gas giant in our solar system, due to its closeness to its host star, which it orbits once every 19 Earth hours. This extreme proximity means WASP 43b is also tidally locked to its star. Now, researchers have discovered that this tidal lock permanently heats one side of the planet to temperatures around 1,260 degrees Celsius, hot enough to melt iron. This scorching heat vaporizes rock and carries it into clouds. The temperature difference between the day and night side, which is comparatively cooler at 600 degrees Celsius, drives fierce winds that can reach speeds of up to 9,000 kilometers per hour, the scientists found. To gauge the temperature of the planet, the researchers used Webb's MIRI to measure light from the system every 10 seconds for more than 24 hours. According to lead author Taylor Bell, a researcher at the Bay Area Environmental Research Institute in San Jose, California, by observing over an entire orbit, we were able to calculate the temperature of different sides of the planet as they rotate into view. From that, we could construct a rough map of temperature across the planet. Webb's infrared measurements also revealed the planet's chemical composition, which includes water vapor, but lacks methane. Methane is usually produced on planets of this type via reactions between hydrogen and carbon monoxide, but the planet's fierce winds may be carrying this methane to the planet's day side, where it is destroyed by its host star's fierce radiation. Following up on the current findings, another team is using the James Webb NIRSpec instrument to improve the temperature map and measure the carbon monoxide in the two-faced planet's atmosphere. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. When it comes to the origin of the universe, the first reaction in many people's minds is the Big Bang. Currently, this is the most widely accepted theory, suggesting that about 13.8 billion years ago, the universe exploded from a singular point with maximum density and extreme heat, continuously expanding over a long period and evolving to its current state. Therefore, according to this theory, scientists always believed that the early universe was a chaotic place, filled with masses of matter that could form crystals, all very disorderly. However, there are still many hypotheses surrounding the somewhat mythical story of the birth of an entire universe. Among them, the most frequently asked question is, are we alone in this vast space? If not, what lies beyond the borders, where light and all space come to an end? Could it be another universe or a different epoch? Looking back over billions of years, these scientists can observe the evolution of our universe in astonishing detail. From there, they open the door to a new realm with 5 hypotheses about what might exist beyond the boundaries of our universe. What is the observable universe? If we want to know what lies beyond the universe, we first need to determine the nature, shape, and size of the universe. If we were to envision a specific state of the universe, many people would choose the image of a large, spherical ball, round and filled with matter. The outer shell of this spherical ball is the boundary, and nothing can surpass it, not even light. Isn't that peculiar? If the universe were a solid, stationary sphere, such a scenario would never occur. However, through the process of observation, humans have discovered that the universe is undergoing expansion at an acceleration faster than the speed of light. That's why we develop and maintain the concept of the observable universe. The observable universe for humans on Earth is a region of space that encompasses all matter, objects, and phenomena that humans, with astronomical instruments, can observe at present. It includes systems of galaxies, galaxy clusters, stars, black holes, and more. Since we can only see things when their light reaches us through emission or reflection, we can never observe beyond the farthest distance that light can travel during the existence of the universe. This means that the observable universe is expanding, but it has a limit. This quantity is sometimes referred to as the Hubble volume, named after the telescope that has provided us with the farthest views of the universe. We will never be able to see beyond that boundary. So in terms of intentions and purposes, it is the only universe we have ever interacted with. People often estimate the overall size of the universe by estimating the number of galaxies existing in observable space. According to NASA, the number of galaxies in the universe has increased tenfold compared to previous estimates by scientists. Utilizing the Hubble Space Telescope, NASA has discovered more galaxies. Around the 1990s, based on the information gathered, humans only estimated about 200 billion galaxies in the universe. Using a new mathematical model, the research team calculated and deduced the number of galaxies that even the most advanced astronomical telescopes have not detected. About 90% of galaxies in the universe cannot be seen because they are too faint or too far from our planet. Therefore, the current number of galaxies in the universe may have reached 2 trillion, 10 times the previous estimate. According to scientists, the universe is expanding, and our Milky Way galaxy has around 100 billion stars. If multiplied by the figure of 2 trillion galaxies, there would be approximately 200,000 trillion stars in the entire universe. Even this number is likely too small, as we may discover many more galaxies in the future with further technological advancements. Hubble volume. Like everything else in physics, our universe strives to exist in the lowest possible energy state. However, around 10 to 36 seconds after the Big Bang, cosmologists speculate that the universe found itself in a false vacuum state. When searching for the actual lowest point of the vacuum energy in a fraction of a moment, the universe is believed to have inflated by a factor of 1050. Since then, our universe has continued to expand, but much slower. We observe evidence of this expansion in the light from distant objects. As photons emitted by a star or galaxy travel throughout the universe, the space's expansion causes them to lose energy. By the time these photons reach us, their wavelengths have shifted towards the red end of the spectrum, corresponding to the distance they have traveled. This is why astrophysicists talk about redshift as a function of both distance and time. Light from these distant objects has traveled for so long that when we finally see it, we are observing those objects as they existed billions of years ago. Redshifted light allows us to see objects like galaxies when they existed in the distant past, but we cannot see all events that have occurred in our universe throughout its history. Because our universe is expanding, light from some objects is too far away for us to see. The physical nature of that boundary partly depends on a quantity of both space and time called the Hubble volume. Here on Earth, we determine the Hubble volume by measuring something called the Hubble parameter, H0, a value related to the apparent recession velocity of distant objects with their redshift. It was first calculated in 1929 when Edwin Hubble discovered that galaxies in the distant cosmos seemed to be moving away from us at a rate proportional to the redshift of their light. The result was a contentious revelation that the universe is expanding with an acceleration faster than the speed of light. This is also one of the fascinating consequences following the theory of general relativity that we've discussed extensively before. Revisiting the issue of the observable universe, in cosmology, a Hubble sphere is the region of the universe observable surrounding an observer, where objects are receding from the observer at a speed greater than the speed of light due to the universe's expansion. However, the volume of the Hubble sphere is not identical to the observable universe. To understand this, consider that as the universe ages, distant light has more time to reach our detectors on Earth. We may observe objects that have accelerated beyond our current Hubble volume because the light we see today was emitted when they were still within it. To be precise, our observable universe aligns with what is known as the particle horizon. The particle horizon marks the distance to the farthest light that we can currently see, the photons that have had enough time to be within or catch up to our gently expanding Hubble sphere. And how far is this distance? Over 46 billion light-years in every direction, bestowing upon our observable universe an approximate diameter of 93 billion light-years, or over 500 trillion miles. At this point, I have a few clarifications to offer. We should not equate the concept of the particle horizon with the concept of the event horizon of the universe. The particle horizon encompasses all events in the past that we can currently observe. On the other hand, the event horizon of the universe defines a distance where an observer in the future will be able to see ancient light emitted by our tiny slice of time today. In other words, the particle horizon refers to the distance to objects in the past whose ancient light we can see today. The event horizon of the universe refers to the distance that our current light can travel as the remote regions of the universe accelerate away from us. Thanks to the expansion of the universe, there are regions that we will never see, even if we were to wait an infinite amount of time for their light to reach us. But what about areas beyond the reach of today's Hubble telescope? If that sphere is also expanding, can we see objects at its boundary? This depends on which region is expanding faster, the Hubble volume or the parts of the universe just beyond it. The answer to this question relies on two factors. One, whether H0 is increasing or decreasing, and two, whether the universe is accelerating or decelerating. These two ratios are closely related, but they are not the same. In reality, cosmologists believe that we are currently in a time when H0 is decreasing. However, due to dark energy, the rate of expansion of the universe is increasing. It may sound counterintuitive, but as long as H0 is decreasing at a slower rate than the rate at which the expansion of the universe is accelerating, the overall motion of galaxies moving away from us continues to occur at a faster pace. At this moment, cosmologists believe that the expansion of the universe will surpass the modest growth of the Hubble volume. Therefore, even though our Hubble volume is expanding, the influence of dark energy seems to impose a rigid limit on the ever-increasing observable universe. What will exist outside the Hubble volume? Royal Astronomer of the UK, Martin Rees, suggests that the theory of eternal inflation could lead to a fourth Copernican revolution. After Copernicus proposed that Earth is just one of many planets orbiting the Sun, we realized that the Sun is also just one of countless stars in the Milky Way, and other stars also have planets orbiting them. Further discoveries led us to understand that the Milky Way is just one galaxy among myriad galaxies in an expanding universe. And now, even the entire universe might be just one among countless universes. Although there is no conclusive evidence for the accuracy of this theory, eternal inflation could help address one of the most challenging issues in modern physics. Physicists have long sought a theory of everything, or the grand unified theory, a set of laws, or even just a simple equation that can be used to derive all other physical laws. However, the possibilities they explore outnumber the fundamental particles in the universe. The string theory, a viable candidate for the ultimate theory, has an enormous number of solutions, one followed by 500 zeros. Each solution establishes its own set of physical laws, and there is no clear reason to choose one over the others and disregard the rest. The theory of multiverse inflation frees us from the burden of choice. Each universe within it may have different physical laws determined by one or a few solutions of string theory. In the universe we inhabit, fundamental physical constants seem finely tuned to allow for the existence of life. For instance, slight variations in electromagnetic forces would render atoms unstable. A mere 4% change in this force would halt all nuclear reactions in stars, essential for producing carbon atoms for living organisms. Similarly, there is a delicate balance between gravitational forces contracting the universe and dark energy expanding the universe to allow stars to form without the universe collapsing. These mysteries have led many to believe in the divine hand of God. However, if the multiverse inflation is true, every set of physical laws could be valid somewhere, providing an alternative explanation. In each universe, there would be a suitable configuration for a form of life to develop. Intelligent beings would then strive to understand their fortunate circumstances. In universes with configurations unsuitable for life, no one would ponder these questions. This is an example of the anthropic principle. If things were not as we observe them, we wouldn't be here to ask questions. For many physicists and philosophers, this seems like an evasive way of addressing the issue. How can one test these assertions? However, unless you have an alternative explanation for the natural laws, some will argue that every occurrence is due to the hand of God. Astronomer Bernard Carr boldly stated, "If you don't believe in God, you should believe in the multiverse." Astronomers suggest that space may be infinite, with stuff, energy, galaxies, etc., distributed somewhat similarly to the observable universe. If this is true, it has some incredibly strange implications. for what lies beyond. Beyond the Hubble volume, you would not only find many different planets. Eventually, you will find everything imaginable. This also aligns with the saying, if you go far enough, you'll find another solar system with an Earth exactly like ours in every aspect, except this morning you had cereal instead of eggs. And in another case, you skipped breakfast. And in yet another, you woke up early and robbed a bank. In reality, cosmologists believe that if you go far enough, you'll find another Hubble volume entirely identical to ours. There's another version of you out there reflecting every action you take, about 10 to the power of 188 meters away. It may sound far-fetched, but the universe is infinitely mysterious, hiding things beyond the limited perception of humans. In astrophysics, the dark flow is a non-random component in the theoretical peculiar velocity of galaxy clusters. According to standard universe models, the motion of galaxy clusters relative to the cosmic microwave background should be randomly distributed in all directions. However, a group of astronomers led by Alexander Kashrinsky, analyzing 3 years of data from the Wilkinson Microwave Anisotropy Probe, WMAP, using the Sunyaev-Zeldovich dynamic effect, found evidence of a galaxy cluster flow surprisingly consistent with a velocity of 1,000 kilometers. This flow was discovered shifting towards the Centaurus and Hydra superclusters. This aligns with the orientation of the Great Attractor, a gravitational anomaly first discovered in 1973. However, the gravitational force of the Great Attractor is believed to originate from a massive galaxy cluster called the Norma cluster located about 250 million light-years from Earth. In a study in March 2010, Kashrinsky expanded his work from 2008, using the results of WMAP's 5-year data instead of the 3-year data and doubling the number of observed galaxy clusters to 700. The research team also divided the cluster catalog into 4 slices, representing different distance ranges. So far, researchers have listed its effects up to 2.5 billion light-years and hope to extend the catalog further to double the current distance. Some researchers suggest that this motion could be remnants of the effects of an unseen region in the pre-inflationary universe. Telescopes cannot observe events earlier than about 380,000 years after the Big Bang, cosmic microwave background, when the universe became transparent. This corresponds to the particle horizon at a distance of about 46 billion light-years. The matter causing the net motion in this proposal lies beyond this range. Thus, in some way, it exists outside our observable universe. However, it would still be within our previous light cone. This motion challenges any predictions about the mass distribution throughout the universe after the Big Bang. Some have speculated that large structures outside the Hubble volume might have caused gravitational influences. This implies that the structure of the infinitely extending universe beyond our sight is non-uniform. For these structures themselves, they could be anything in the literal sense, from aggregations of matter and energy on scales we can hardly imagine to strange curved paths conveying gravitational effects from other universes. Based on the data, Laura Mersini-Horton and Rich Holman observed that some anomalies predicted by both theories related to interactions with alternate universes, or when the reference frame of the CMB does not match the expansion frame of the universe. In 2013, arguments were made that data from the Planck satellite of the European Space Agency showed no statistically significant evidence for the existence of dark flows. However, another analysis by Fernando Atrio Vallandera, a member of the Planck collaboration, argued that this data was consistent with previous findings from WMAP. Mainstream media continued to show interest in this idea, with Mersini-Horton claiming that the Planck results confirmed the existence of a multiverse. This could be an effect of a sibling universe or an entirely different space-time region compared to the observable universe. Data from over 1,000 galaxy clusters have been measured, including clusters located up to 3 billion light-years away. Alexander Kashrinsky argued that these measurements show a stable flow in the universe not due to statistical luck. The only thing we can say for certain is that the world in a very distant place is very different from the world we see on Earth. It's either another universe or a different space-time structure. Infinite bubbles. Talking about what's beyond the Hubble volume might be a bit tricky because it could still be the same universe or just a part of it that we cannot see. It would have all the same laws and physical constants. In another version of the story, the expansion of the universe after the Big Bang led to the formation of bubble structures in the space-time fabric. Each bubble is a region where the expansion halts along with the rest of space and forms its universe with its own set of laws. In this scenario, space is infinite, and each bubble is also infinite, as you can fit an infinite number of infinities within a single bubble. Even if somehow you could cross the boundary of our bubble, the void between the bubbles is still expanding, so you'd never reach the next bubble no matter how fast you travel. The simplest multiple universes model stems from the assumption of the universe's infinity. While we can't confirm this hypothesis, we can't deny it either. According to this idea, the universe is divided into many separate regions, each unable to detect the others due to the vast size of the universe. The estimated age of the universe is about 13.8 billion years, so anything beyond the 13.8 billion light-year range is indistinguishable. Each such region can be considered its universe. If this is true, there would be countless universe islands similar to the universe humans are familiar with, and there must be many worlds similar to Earth. It may sound implausible that atoms would arrange the same way to create a copy of Earth, or a copy with only minor details different. However, if the infinity of worlds is real, such a place must exist, and there could be many. With the same logic, there should be a copy of our universe very far away, at a distance of about 10 to 10, 118 meters. However, it could also be a finite universe. In the case of an infinite universe, matter could only concentrate in a corner of the universe, meaning other places would be mere emptiness. But, as of now, there is no clear evidence for this hypothesis. Another model of multiple universes, which can be seen as a solution to the fine-tuning problem without resorting to the anthropic principle, is the natural selection of universes proposed by Lee Smolin from the Perimeter Institute for Theoretical Physics in Waterloo. In 1992, he suggested that the universe could reproduce and evolve like living organisms. On Earth, natural selection preserves organisms with useful traits, well suited to the environment for growth and development. Smolin argued that a similar phenomenon occurs in the universe, called cosmic natural selection. The idea is that a mother universe can give rise to many child universes within it. The mother universe achieves this through black holes. A black hole forms when a massive star collapses under its gravitational force, squeezing atoms together until reaching infinite density. In the 1960s, Stephen Hawking and Roger Penrose demonstrated that this collapse is akin to the reverse of a mini Big Bang. This idea led Smolin to believe that a black hole could be a Big Bang, giving birth to a new universe within it. If so, the new universe might have slightly different physical properties than the universe containing the original black hole. This is analogous to random genetic mutations leading to offspring that differ from their parents. If the physical laws in the child universe allow for the formation of atoms, stars, and life, it would also have black holes with the potential to give rise to new universes. Over time, the number of such universes would increase, becoming more prevalent than universes without black holes or the ability to reproduce. This is an intriguing idea, suggesting that our universe doesn't have to be a product of sheer randomness. If a finely tuned universe, capable of forming atoms and life, is surrounded by untuned universes, cosmic natural selection implies that the finely tuned universe will gradually become the norm. This model has a significant advantage. It can be tested. We can search for the specific conditions of this universe conducive to black hole formation. However, so far, there is no evidence that black holes can give rise to an entirely new universe. As we delve into the realms of the bizarre and the mind-bending, one thing becomes clear. Our understanding of the universe is just scratching the surface. The 5 weird theories we've explored today challenge the very fabric of our comprehension, pushing us to question the limits of existence itself. Whether it's the idea of a cosmic hologram projecting our reality, parallel universes existing in tandem, or the universe being a mere simulation played out in some advanced cosmic computer, these theories invite us to embrace the mystery that shrouds the cosmos. It's a reminder that the universe is not a stagnant entity, but a dynamic, ever-evolving enigma that keeps us on the edge of our intellectual seats. As we navigate the vastness of these peculiar speculations, it's essential to approach them with both curiosity and skepticism. The quest to unravel the secrets beyond our universe continues, fueled by the human spirit's insatiable thirst for knowledge. Whether these theories turn out to be flights of fancy or the keys to unlocking the universe's deepest truths, one thing remains certain. The cosmos will keep us guessing, inspiring generations to come on a journey into the great unknown. So, as we conclude this exploration, let's marvel at the mysteries that lie beyond the universe and eagerly anticipate the discoveries that await us on the cosmic horizon. The James Webb Space Telescope has propelled us into a new era of space exploration, granting us unprecedented access to the wonders of the cosmos. Through its remarkable images and scientific achievements, it has expanded our understanding of the universe and ignited our collective curiosity. The time machine embodies the spirit of human ingenuity and exploration as we continue to push the boundaries of what we know and embark on a journey towards unlocking the mysteries of the universe. The clarity and detail of Webb's images have stunned both scientists and the general public alike. With its remarkable resolution and sensitivity, the premier observatory has allowed astronomers to study the formation of stars and galaxies with unparalleled accuracy. By capturing infrared light, it has unraveled mysteries that were previously inaccessible, shedding light on the early stages of the universe's evolution. Join us as we dig deep into how James Webb just unveiled early the universe is different than we thought. For 380,000 years after the Big Bang, the cosmos was a hot, dense mixture of protons, electrons, other elementary particles, and light elements. But the expanding universe was cooling fast. And once the temperature dropped to about 3,000 kelvins or 2,530 degrees Celsius, protons and electrons were able to form atoms. Not all atoms, mind you. No gold was floating around, or aluminum, or even elements as light as oxygen. Hydrogen and its heavy isotope deuterium accounted for about 3/4 of everything. A couple of isotopes of helium accounted for most of the other quarter. And a tiny fraction, about 1/billionth of everything, of lithium had also been produced. Just because brand new hydrogen and helium were swirling about doesn't mean stars were popping into existence. In fact, the first of those luminous objects didn't appear until the universe was about 100 million years old. So, for a span of time longer than the dinosaurs have been extinct on Earth, there were no stars or galaxies, or, for that matter, any objects emitting light. It's out of this darkness that astronomers are trying to piece together the origin of the first generation of stars, called Population 3 stars. As brightly as they shone, their light is now too faint to be detected by current observatories, and even the next generation of telescopes will struggle to spot them. But through scientific detective work, astronomers are beginning to understand how these elusive objects lived and died. A major clue comes courtesy of the cosmic microwave background, the relic radiation that formed in the hot, early universe. This radiation has been cooling ever since it was emitted as the cosmos expands. Currently, the background temperature is about 2.73 kelvins or minus 270 degrees Celsius. And measurements of the cosmic microwave background show that it is incredibly consistent, corresponding to density variations of only 1 part in 100,000. But those variations, literal ripples in the structure of the universe, are revealing how the first stars formed. Computer models show that the minuscule density fluctuations in the early universe acted as starting points for immense clouds of gas. Without these variations in structure, nothing would have formed. The whole cosmos would have evolved into an ever-thinning homogeneous cloud of hydrogen, helium, and that tiny bit of lithium. However, thanks to gravity, the fluctuations became gathering points, huge clouds where gas continued to collect. Eventually, the clouds contracted. As they did, they heated up to 1,000 kelvins, which equals more than 700 degrees Celsius. That temperature would be far too high for a star-forming region today to form stars. Indeed, if a cloud is hotter than about 10 kelvins or minus 263 degrees Celsius, the speed of the atoms inside it will be too fast for them to stick together and eventually form stars. But the clouds in the early universe were larger and much more densely packed than modern-day nebulae. Within them, some hydrogen atoms paired up to become hydrogen molecules. And because molecules are better emitters of infrared radiation, heat, the temperature dropped and clumps inside the clouds could contract further. Each of the regions was probably several hundred times as massive as the Sun. That much mass and its corresponding gravity could overcome the outward pressure from radiation. The clumps didn't split as they contracted, so only a single star formed from each one. The result was that the first stars were potentially colossal. Estimates range from several tens of solar masses up to 1,000 solar masses, and luminous perhaps millions of times as bright as the Sun. Because the universe was smaller and denser, vast numbers of these stars formed near each of its density variations. Eventually, the gravitational pull from these stars would attract other stars, and the numbers grew from there. Astronomers think this took a few 100 million years, but at the end of that time, the first galaxies had formed. You may be wondering how anyone could figure out how stars formed during a time when the universe was unobservable. Fortunately, the cosmos wasn't as complex then as it is now, making it simpler for cosmologists to model. Theorists started imagining these first fireballs named Population 3 in the 1970s, hypothesizing that after short lifetimes they exploded as supernovas, forging heavier elements and spewing them into the cosmos. That star stuff later gave rise to Population 2, stars more abundant in heavy elements. Then even richer Population 1, stars like our Sun, as well as planets, asteroids, comets, and eventually life itself. As Rebecca Bowler, an astronomer at the University of Manchester in the United Kingdom said, "We exist, therefore we know there must have been a first generation of stars." And now, a group of astronomers poring over data from the James Webb Space Telescope has just revealed that our $10 billion time machine finally found them. The Supreme Space Observatory has glimpsed light from ionized helium in a distant galaxy, which could indicate the presence of the universe's very first generation of stars. James Webb, Space Telescope's Advanced Deep Extragalactic Survey, or JDS, has been allocated a month of Webb's observing time, spread out over 2 years, and takes advantage of the telescope's unprecedented sensitivity to investigate the earliest galaxies in greater detail than ever before. In December 2022, the Premier telescope discovered the most distant, and therefore earliest, galaxies ever found, at least up to that point. The light from these galaxies set out when our universe was just 2% of its current age and has taken the last 13.4 billion years to reach us. JD's focused James Webb's sharp infrared eyes on the same patch of sky as Hubble's ultra-deep field, located in the Fornax cluster. While Hubble found an impressive 10,000 galaxies in the region, Webb's image is 15 times larger and contains a staggering 100,000 galaxies. Astronomers are still sifting through this deluge, looking for the most distant galaxies among them. One easy way to pick out distant candidates is to use the fact that hydrogen gas absorbs almost all light at wavelengths shorter than 91 nanometer, called the Lyman limit. Since galaxies are filled with hydrogen, this creates a sharp step in their ultraviolet and X-ray emissions. However, as light travels through space, it is stretched, or redshifted, due to the expansion of the universe. The longer it travels, the more it stretches, until this step in emissions moves into the visible range. Astronomers can use the position of this Lyman break to work out how far away a galaxy is. For 28 hours over 3 days, James Webb collected the faintest infrared spectra ever taken from 250 candidate galaxies, revealing the precise position of the Lyman break in each galaxy. This confirmed that 4 of the galaxies had a redshift above 10, setting new distance records, including 2 with redshifts of 13. In several different regions of the sky, James Webb found little red dots corresponding to galaxies that appeared to be at more astonishing redshifts: 14, 17, even 20. Some of the galaxies seemed small and dim as expected, but others looked big and bright, suggesting they were heftier than astronomers would expect for such early galaxies. The huge galaxy haul raises another question. How many of them are likely to be at such great distances? A potential record-breaking galaxy called Sears 93316 is a cautionary tale. The galaxy was identified in Webb's images taken for the Cosmic Evolution Early Release Science, or Sears survey. Those images put the galaxy at a photometric redshift of 16.4, or just 240 million years after the Big Bang. According to Finkelstein, the survey's lead researcher, that was higher redshift than we expected to see. As a result, one set of impossible early galaxies has sparked debate over not just galaxy formation, but the theoretical foundations of the universe itself. Nothing that massive should have been able to form that fast. It calls the whole picture of early universe into question. That's also why scientists affectionately calls them the universe breakers. In short, the world's most powerful telescope is rewriting the story of space and time. It pulls back the shroud on the earliest galaxies, which are more numerous and brighter than expected, revealing our early universe is not quite like how we might have predicted. Notably, based on unexpected discoveries from the James Webb, Xin Wang, an astronomer at the Chinese Academy of Sciences in Beijing, and his colleagues unveiled that they have spotted the universe's first stars. "It's really surreal," Wang said. Wang's team analyzed spectroscopy data for more than 2,000 of James Webb's targets. One is a distant galaxy seen as it appeared just 620 million years after the Big Bang. According to the researchers, the galaxy is split into 2 pieces. Their analysis showed that one half seems to have the key signature of helium-2 mixed with light from other elements, potentially pointing to a hybrid population of thousands of population 3 and other stars. Spectroscopy of the second half of the galaxy has yet to be done, but its brightness hints at a more population 3 rich environment. As Wang said, "We are trying to apply for observing time for James Webb Space Telescope in the next cycle to cover the entire galaxy in order to have a shot of confirming such objects." But according to Mike Norman, a physicist at the University of California, San Diego, the galaxy is a head-scratcher. If the helium-2 results stand up to scrutiny, one possibility is a cluster of population 3 stars. However, he's unsure if population 3 stars and later stars could mix together so readily. Daniel Whalen, an astrophysicist at the University of Portsmouth, was similarly cautious. He said that it definitely could be evidence of a mixture of population 3 and population 2 stars in one galaxy. However, note that although this would be the first direct evidence of the universe's first stars, it's not clean evidence. Other piping hot cosmic objects can produce a similar helium-2 signature, including scorching disks of material that swirl around black holes. Wang thinks his team can rule out a black hole as the source because they did not detect specific oxygen, nitrogen, or ionized carbon signatures that would be expected in that case. However, the work still awaits peer review, and even then, follow-up observations will need to confirm its potential findings. Other groups using James Webb are also hunting for the first stars. Besides looking for helium-2, another search method, proposed by the astronomer Rogier Windhorst of Arizona State University and colleagues in 2018, is to use the gravity of giant clusters of galaxies to see individual stars in the early universe. Using a massive object, like a cluster, to warp light and magnify more distant objects, a technique known as gravitational lensing, is a common way astronomers obtain views of distant galaxies. Windhorst believed that even individual population 3 stars approaching the edge of a heavy cluster could in principle undergo nearly infinite magnification and pop into view, he said. Windhorst leads a James Webb program that is attempting the technique. He's pretty confident that in a year or two, we will have seen some. We already have some candidates. Similarly, Eros Vanzella, an astronomer at the National Institute for Astrophysics in Italy, is leading a program that's studying a clump of 10 or 20 candidate population 3 stars using gravitational lensing. We are just playing with the data now, he said. And there remains the tantalizing possibility that some of the unexpectedly bright galaxies already seen by James Webb in the early universe could owe their brightness to massive population 3 stars. As Vanzella said, these are exactly the epochs where we expect the first stars are forming. I hope that in the next weeks or months, the first stars will be detected. Interestingly, in addition to reveal details of the universe just after its Big Bang birth 13.8 billion years ago, and images of stars being born in dust clouds, James Webb is also providing science with a further gift. Its infrared eyes also turns out to be ideal for studying extrasolar planets, or exoplanets, as worlds that orbit other stars are known. In doing so, the Webb telescope is triggering an astronomical revolution. For centuries, the only planets known to humans were the few we could see in our solar system. But was the Sun's family typical, scientists wondered? Were planets plentiful elsewhere in the galaxy, or were they rare? These questions were of crucial importance because the latter scenario, a cosmic paucity of planets, would mean extraterrestrial life was also likely to be scarce. The trouble for astronomers was the simple fact that stars are very bright, but planets are much smaller and very much dimmer, and could not be detected beside their brilliant celestial parents. It was not until the end of the last century that a new generation of highly sensitive cameras, fitted to telescopes and orbiting observatories, were able to pinpoint the slight dimmings caused by exoplanets as they passed in front of stars. After the first few of these transit observations were made, discoveries began to multiply dramatically. Today, the total number of observed exoplanets stands at 5,506, according to NASA's Extrasolar Planet Archive. Crucially, several hundred are relatively close to Earth, and these are now ripe for study with the James Webb. There is a distant world where quartz crystals float above a searing hot, puffy atmosphere. Vaporized sand grains, not water droplets, form the clouds that fill the sky on WASP 107b, a planet 1,300 light-years from Earth. Then there is GJ 1214, the Sauna planet. With a mass 8 times that of Earth, it orbits its parent star at a distance that is 1/70th of the gap between Earth and the Sun, and seems to be coated in a thick, dense atmosphere containing vast amounts of steam. Or there are the giant Jupiter-sized planets of the Orion Nebula, which have been discovered free-floating in space, rogue worlds that appear to be unconnected to any parent star, to the bafflement of astronomers. These strange, remote planets could not be more diverse or dramatically different from each other, although they do share one common feature. Their wonders are now being revealed by the James Webb Telescope. But when it comes to detecting the presence of liquid water on planets outside the solar system, and thus the conditions needed for life, the James Webb Space Telescope might want to looking for what is missing rather than what is there. A team of researchers, including scientists from the Massachusetts Institute of Technology and the University of Birmingham, suggest that if rocky worlds like Earth outside the solar system have a lower quantity of carbon dioxide in their atmospheres than other planets in the same system, this could be a sign they harbor liquid water. And as we know from the formation of life on our own planet and the conditions needed to support life here, the presence of liquid water is a key indicator of potential habitability. Whereas looking for key chemical components that indicate habitability on extrasolar planets, or exoplanets, is only just within reach of current technologies, depleted carbon dioxide is a signature James Webb is now ready to spot. As Julian DeWitt, Discovery team member and an assistant professor of planetary sciences at the Massachusetts Institute of Technology, said in a statement, "The holy grail in exoplanet science is to look for habitable worlds and the presence of life. But all the features that have been talked about so far have been beyond the reach of the newest observatories. Now we have a way to find out if there's liquid water on another planet, and it's something we can get to in the next few years." Currently, scientists are very good at using instruments to determine how far a planet is from its host star, and thus whether it is in that star's habitable zone, defined as the region that's neither too hot nor too cold to allow for the existence of liquid water. In our own solar system, however, Earth, Mars, and even Venus are all in the habitable zone around the Sun. Yet, only one of those planets currently has the capability to support life as we know it. That means habitability and preserving liquid water for exoplanets isn't all location. So, currently, scientists don't have a robust way of confirming if a planet is habitable or not. Thinking about Earth, Mars, and Venus, as well as the differences between the trio, the team realized that the only one with habitability, Earth, also has an atmosphere depleted of carbon dioxide in comparison to its habitable zone neighbors. Triad pointed out that we assume that these planets were created in a similar fashion, and if we see one planet with much less carbon now, it must have gone somewhere. The only process that could remove that much carbon from an atmosphere is a strong water cycle involving oceans of liquid water. Over the course of billions of years, our planet's oceans have been responsible for depleting huge amounts of carbon dioxide from the atmosphere, meaning it has less now than Venus or Mars. As Frieder Klein, research co-author and a scientist at the Woods Hole Oceanographic Institution, said in the statement, "On Earth, much of the atmospheric carbon dioxide has been sequestered in seawater and solid rock over geological timescales, which has helped to regulate climate and habitability for billions of years. That led the team to think that a similar depletion of carbon dioxide in an exoplanet's atmosphere could also indicate the presence of a liquid ocean. Conducting a search with these parameters would be best suited to peas-in-a-pod planetary systems that, like the solar system, host multiple rocky or terrestrial worlds of similar sizes that orbit their star at similar distances. The first step in the investigation suggested by the team is to hunt for carbon dioxide and use this as an indicator that the exoplanet targets have an atmosphere. Once multiple planets in a single system are determined to have atmospheres, the next step would be to determine just how much carbon dioxide is in the atmospheres. This should reveal if one or more of the planets have significantly less carbon dioxide than the others, indicating that it likely has oceans of liquid water and could thus be habitable. Of course, there is a little more to this method than just comparing carbon dioxide abundances. Habitability doesn't equal inhabited. To check if life may actually exist on an exoplanet highlighted by a lack of carbon dioxide, the team suggests looking for another molecule, ozone. Composed of 3 oxygen atoms, ozone is a molecule created when life forms like plants and microorganisms strip carbon dioxide from the atmosphere of Earth, then emit oxygen molecules that are struck by sunlight. Ozone is a good gauge of these processes on alien worlds because it is easier to detect in the atmosphere of distant exoplanets than oxygen itself is. The team says that if a planet's atmosphere shows signs of depleted carbon dioxide coupled with an abundance of ozone, then it could well be both habitable and inhabited. According to Triad, if we see ozone, chances are pretty high that it's connected to carbon dioxide being consumed by life. And if it's life, it's glorious life. It would not be just a few bacteria. It would be a planetary-scale biomass that's able to process a huge amount of carbon and interact with it. The researchers believe the Webb telescope is already capable of measuring abundances of carbon dioxide and ozone in multi-planet systems close to Earth. This includes the TRAPPIST-1 system, located 40 light-years away, which is known to host 7 Earth-like planets, several of which are in the habitable zone of their cool star. As DeWitt concluded, TRAPPIST-1 is one of only a handful of systems where we could do terrestrial atmospheric studies with the James Webb Space Telescope. Now we have a roadmap for finding habitable planets. If we all work together, paradigm-shifting discoveries could be done within the next few years. The team's research was published on December 28 in the journal Nature Astronomie. After all, astronomers using James Webb to seek out signs of extraterrestrial life are looking for a set of biological markers known as the Big Four: oxygen, carbon dioxide, water, and methane. Their presence in the atmosphere of an exoplanet would be a strong sign that life of some kind exists there. Maybe someday, we'll learn whether riotous jungles cover alien landscapes, whether otherworldly insects swarm in faraway atmospheres, and whether extraterrestrial rivers and seas also cradle life. The first step is getting to know our exoplanetary neighbors, and James Webb is helping us see them in more detail than ever before. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. From its perch about 1 million miles from Earth, James Webb has captured extraordinary shots of our solar backyard, while also peering deep more than 13 billion years into the past, at an era when some of the first stars and galaxies were taking shape. But as James Webb delved deep into the first chapter of the cosmic history book, it found unexpected shreds of evidence that shake our cosmology. Look at unprecedented images of the early universe taken by James Webb. Nobody can still hold on to old theories and claim that they are still true. Webb's discoveries present a serious challenge to our best model of how the cosmos evolved. But is the standard model of physics now broken? Join us as we dig deep into how James Webb's view of the ancient universe just shatters our basic understanding of the cosmos. The first billion years of the universe's life were a crucial period in its evolution. In the first moments after the Big Bang, matter and light were bound to each other in a hot, dense soup of fundamental particles. However, a fraction of a second after the Big Bang, the universe expanded extremely rapidly. This expansion eventually allowed the universe to cool enough for light and matter to separate out of their soup and, some 380,000 years later, form hydrogen atoms. The hydrogen atoms appeared as an intergalactic fog, and with no light from stars and galaxies, the universe was dark. This period is known as the Cosmic Dark Ages. the arrival of the first generations of stars and galaxies several 100 million years after the Big Bang bathed the universe in extremely hot UV light which burned or ionized the hydrogen fog. This process yielded the transparent, complex, and beautiful universe we see today. Astronomers call the first billion years of the universe, when this hydrogen fog was burning away, the epoch of reionization. To fully understand this time period, we study when the first stars and galaxies formed, what their main properties were, and whether they were able to produce enough UV light to burn through all the hydrogen. The first step toward understanding the epoch of reionization is finding and confirming the distances to galaxies that astronomers think might be responsible for this process. Since light travels at a finite speed, it takes time to arrive to our telescopes, so astronomers see objects as they were in the past. For example, light from the center of our galaxy, the Milky Way, takes about 27,000 years to reach us on Earth, so we see it as it was 27,000 years in the past. That means that if we want to see back to the very first instance after the Big Bang, we have to look for objects at extreme distances. Because galaxies residing in this time period are so far away, they appear extremely faint and small to our telescopes and emit most of their light in the infrared. This means astronomers need powerful infrared telescopes, like Webb, to find them. Prior to Webb, virtually all of the distant galaxies found by astronomers were exceptionally bright and large, simply because our telescopes weren't sensitive enough to see the fainter, smaller galaxies. However, it's the latter population that are far more numerous, representative, and likely to be the main drivers to the reionization process, not the bright ones. So, these faint galaxies are the ones astronomers need to study in greater detail. It's like trying to understand the evolution of humans by studying entire populations rather than a few very tall people. By allowing us to see faint galaxies, Webb is opening a new window into studying the early universe. Early galaxies were not like those we know today. The first galaxies were more pristine, composed primarily of hydrogen and helium gas. Over time, their stars would fuse atoms to form heavier elements, and when these stars died in supernova explosions, the heavy elements dispersed throughout the galaxies, enriching them with star stuff, including the elements needed to create life. The first galaxies had yet to settle into majestic spiral patterns or puffy elliptical balls like the galaxies we see around us now. They were far more disordered and much smaller, making them even harder to find. The earliest galaxies we have seen were about 1% the size of our Milky Way, but they were growing rapidly, forming new stars at prodigious rates. Fuel was plentiful back then. Early galaxies were bathed in cool streams of flowing hydrogen gas, lured inward by gravity. The galaxies collided with one another and merged frequently, accelerating their growth and triggering new bursts of star formation. As the universe expanded over time, galaxy growth slowed, significant mergers became less frequent, and the gas supply thinned out. This picture is our basic understanding of cosmic history. We are still working to fill in the details, and many questions remain, especially surrounding the earliest times. When did the first galaxies form? How small were they? What did they look like? Were they building blocks of galaxies to come with single large regions of star formation? Or were they more fragmented and clumpy? Were they all bursting with intense star formation? Or were some more relaxed, like most galaxies today? Did any early galaxies have time to settle into disks like the Milky Way did? Or were they merging too frequently to do so? Will we ever find any filled with pristine hydrogen and helium gas? Or did the first supernovae enrich them too quickly with heavier elements? How rapidly did early galaxies build up in mass and numbers? And were they in fact responsible for reionizing the universe? With the results from James Webb, we are taking another step toward answering these questions. Thanks to its infrared eyes, James Webb is adding a bounty of distant galaxies beyond Hubble's reach and revealing the early universe in far greater detail than previously possible. Webb's images of the early universe have acted like an ocean swell, delivering new waves of evidence. A new research using the James Webb data found that dwarf galaxies in the early universe often look flat, either prolate, elongated along one axis, or very narrow oblate ovals shaped like a surfboard, whereas others have a more frisbee-like oblate appearance. These galactic frisbees seem to grow more abundant as the universe ages, as do the compact, spheroidal-shaped galaxies. As Viraj Pandya, a Columbia University astronomer and lead author of a new paper describing the research, said in a press statement, roughly 50 to 80% of the galaxies we studied appear to be flattened in 2 dimensions. They seem to be very common in the early universe, which is surprising since they are uncommon nearby. The discovery was made using data from CEERS, or Cosmic Evolution Early Release Science, a James Webb program to push back the veil and probe the lives of the oldest, faintest galaxies in the universe. It's an era spanning from 600 million years after the Big Bang to 6 billion years later, during which the galaxies that we see in the universe around us today formed, evolved, and matured, from spirals like the Milky Way and the Andromeda Galaxy to giant ellipticals such as Messier 87. CEERS builds on previous work by the Hubble Space Telescope, which studied the early universe in its deep field images and its Cosmic Assembly Near-Infrared Deep Extragalactic Legacy Survey program. Hubble found that massive galaxies in the early universe tended to take on the form of oblate spheroids, not dissimilar to the elliptical galaxies of today. Less massive and hence fainter galaxies were more difficult for Hubble to detect, but from what it could see, many of them took on an elongated appearance consisting of chains of brighter blobs, whereas other irregularly shaped dwarfs were nicknamed tadpoles, nuggets, or clumps. The question was, given Hubble's limitations, was it seeing a true reflection of the shapes of smaller early galaxies? The short answer is yes. James Webb's greater vision has now found that Hubble's earlier discoveries hold true. Karthik Iyer, also of Columbia University, described how the greater vision and sensitivity of James Webb, compared to Hubble, is changing the study of galaxies in the early universe. Identifying additional categories for early galaxies is exciting. There's a lot more to analyze now. We can now study how galaxies' shapes relate to how they look, and better project how they formed in much more detail. A picture now emerges of how galaxies may have evolved and grown over time. Matter is distributed throughout the universe primarily in a cosmic web of filaments that span the cosmos. These filaments are predominantly formed from dark matter, with a fraction of normal matter mixed in that forms the galaxies that we observe. The abundance of surfboard-shaped prolate galaxies could be explained by them forming inside halos of dark matter that are elongated in alignment with their cosmic web filament. Since other dwarf galaxies would also be forming within that filament, mergers would take place along it, leading to the growth of elongated galaxies that look like chains. Across billions of years, the cosmic web filaments disperse and grow more diffuse. The merger rate slows down, and the fraction of prolate galaxies decreases as they start to spin and adopt a disk-like, oblate structure. Such oblate galaxies are seen to increase from 20 to 60% over time and for a given mass of galaxy. Similarly, spheroid galaxies also grow more abundant over time, as compact star-forming galaxies in the universe settle down to become the progenitors of the giant elliptical galaxies we see today, or the spheroidal bulges of massive spiral galaxies. Understanding the evolution of galaxies over cosmic history is a key objective of James Webb. The new findings from CEERS indicate that hierarchical mergers, smaller galaxies merging with larger ones, along the aforementioned cosmic filaments, are key to understanding these varied galaxy shapes. But in addition to its stunning pictures, the Webb telescope has also pinpointed puzzling views that were impossible with previous telescopes. For instance, the telescope has spotted several galaxies in the early universe that appear to be utterly gargantuan, with masses ranging from 10 billion to 100 billion times that of our Sun. Put simply, these galaxies shouldn't exist according to rules laid out in the Standard Model. In other words, Webb's discoveries are stress testing the Standard Model of cosmology, also known as the Lambda Cold Dark Matter Model, exposing an important unresolved issue with the properties of galaxies derived from the observations. As Michael Boylan Colchin, a cosmologist at the University of Texas at Austin, said in an email to Motherboard, "The results have been a real surprise for me, and it's been a very exciting period. I have never seen anything like the frenzy of activity and results that accompanied the release of the first data. Indeed, images captured by James Webb are jaw-dropping on a pure aesthetic level, but Boylan Colchin and other scientists have also found many riddles in the telescope's observations, including those massive galaxies that appear some 500 million years after the Big Bang. These objects really do appear to be early behemoths. They are so massive that we do not expect to have enough collections of atomic matter in the universe at that time to give rise to that much stellar content. So how did these galaxies get so big so fast? Webb's observations suggest that the answer may be linked to the rapid growth of supermassive black holes during the same time period. Virtually all modern galaxies contain a supermassive black hole at their centers, including the Milky Way, suggesting that this is a core feature of large galactic structures. If black holes in the early universe were able to grow to huge masses in a short time frame, it might explain why so many massive galaxies are showing up in the telescope's images. However, this explanation essentially trades out one mystery for another. As Boylan Colchin explained, if it does turn out that massive black holes are making these galaxies appear more massive than they truly are, then we will have other puzzles to understand. How did so many black holes grow so massive so quickly in the early universe? On the other hand, it's also conceivable that some unknown mechanism in the early universe supercharged the process of star formation, which could explain why these early galaxies appear so massive and bright. Another mind-boggling possibility is that these galaxies are packed with a group of stars called Population 3, which are the first stars that ever shone in the universe. Spotting these stellar ancestors has been a major goal in astronomy for decades, but it's extremely difficult to see objects that are this far away in time and space. Population 3 stars are expected to be brighter and more massive than their descendants, which hints that they might be hidden away in the strange galaxies seen by James Webb. However, if none of these explanations ultimately fit, it may be time to consider whether these ancient galaxies have exposed a fundamental gap in our understanding of the universe. Perhaps the observations made by James Webb are telling us that our standard and very successful Lambda Cold Dark Matter Model is incomplete, that we're missing a component. There are clues that this is the case. Calculations of the expansion rate of the universe based on measurements at early cosmic epochs don't agree with direct measurements in the local universe, for example. And some proposed solutions to this disagreement, which is called the Hubble tension, involve adding additional dark energy at very early times, only 50,000 years after the Big Bang. An interesting byproduct of these early dark energy models is that they predict faster evolution of structure and more structure at high redshift, which is exactly what would help explain the existence of these massive early galaxies. It is intriguing that a single solution might explain both of these observational discrepancies. In short, one thing is clear. Scientists have their work cut out for them in terms of unraveling the true meaning of these bizarre images. To that end, future observations can help to confirm that these galaxies really are that massive, and astronomers also plan to look at much bigger patches of sky to make sure they aren't seeing a fluke that is limited to one region. However, for now, we will all have to uneasily sit with the unexplained presence of these galactic giants at the edge of space and time. Meanwhile, in another observation made by the Hubble Space Telescope, astronomers have just discovered that the atmosphere of a relatively small planet outside the solar system is rich with water vapor. However, don't plan a vacation to this destination just yet. The planet's surface is hot enough to melt lead, meaning it's a steamy world inhospitable to life as we know it. More specifically, the team behind this finding says the extrasolar planet, or exoplanet, named GJ9872d, exhibits Venus-like temperatures of 752 degrees Fahrenheit or 400 degrees Celsius. But that doesn't make this discovery any less exciting. Though scientists have found water vapor in the atmospheres of many extrasolar planets before, the Hubble telescope's observations of this hot and steamy world, designated GJ9827d, represent the smallest exoplanet around which this vital element for life has been found thus far. As Laura Kreidberg, team member and director of the Max Planck Institute for Astronomy's Atmospheric Physics of Exoplanets department, said, "The discovery of water on GJ9827d is exciting because it's the smallest planet yet where we've detected an atmosphere. It pushes closer than ever to characterizing truly Earth-like worlds." Elsewhere, astronomers has just witnessed 18 ravenous black holes ripping up and devouring stars. This result, made by a team from the Massachusetts Institute of Technology, more than doubles the number of gruesome, star-shredding tidal disruption events seen in the local universe. The findings could help astronomers better estimate the number of tidal disruption events occurring across the universe, bringing the rate closer to theoretical predictions. Tidal disruption events occur when a star gets too close to a black hole, and the latter object's gravitational influence generates tidal forces in the star so great that the stellar body is stretched vertically while squashed horizontally, a process called spaghettification. The material from the star forms a flattened disk around the black hole, with some of it accreting to the black hole's heart, while other stellar matter is channeled to the poles by powerful magnetic fields and blasted out as near-light-speed jets. Previously, astronomers had believed that black holes rip apart and devour stars while blasting out highly energetic jets in galaxies that have recently undergone periods of intense starbirth called starbursts. However, this research implies tidal disruption events can occur across a wider range of galaxies and could help explain the extreme physics seen around such events. As Aaron Kara, team member and an assistant professor of physics at MIT, said in a statement, "People were coming up with very exotic solutions to these puzzles, and now we've come to the point where we can resolve all of them." The MIT team began searching for more star-devouring black holes after they discovered the closest tidal disruption event to Earth ever seen. It was witnessed in the form of a flare from the galaxy NGC 7392, located around 137 million light-years from Earth. This opened up an entirely new way to spot actively feeding black holes, they said. It involves using infrared light and an algorithm that hunts for patterns in infrared data that indicate brief or transient bursts of radiation. The technique completed was based on historical data collected by NASA's Wide Field Infrared Survey Explorer, or NEOWISE for short. Since its launch in 2009, NEOWISE has been searching the sky over Earth for brief bursts of infrared light. The team then cross-referenced the transients they found with a catalog of galaxies within a distance of 600 million light-years of Earth, revealing that the infrared bursts could be traced back to about 1,000 galaxies. Zooming in on these galaxies, the researchers attempted to discover if the signals they had detected came from tidal disruption events, or if they could have been triggered by other violent events, such as the supernova explosion of a massive dying star. It'd also have been possible for them to come from supermassive black holes at the hearts of galaxies as they feed on in falling dust and gas. This ultimately led to the discovery of 18 legitimate tidal disruption event signals that were the result of the gravitational influence of black holes generating tidal forces in stars that eventually led to some gory stellar deaths. Surprisingly, the team found that tidal disruption events seem to occur across a range of galaxies across the entire sky, including ones that are filled with thick clouds of dust. According to research lead author and MIT's Kavli Institute for Astrophysics and Space Research graduate student Megan Masterson, if you looked up in the sky and saw a bunch of galaxies, the tidal disruption events would occur representatively in all of them. In the grand scheme of things, this research helps settle some major questions surrounding tidal disruption events. Previously, astronomers had mainly seen these star-shredding occurrences happening in post-starburst galaxies with stellar factories that had recently shut down. Such galaxies are fairly rare, and scientists were confused as to why tidal disruption events seemed restricted to them. This research alleviates that confusion by finding gory tidal disruption events in a spread of galaxy types. The reason tidal disruption events were seemingly absent from other galaxies is that, whereas post-starburst galaxies are devoid of thick gas and dust because they exhausted the materials, while creating a wealth of new stars, other galaxies still have the material in abundance. Gas and dust are adept at absorbing or blocking optical and X-ray light, but infrared slips through the matter more easily. Thus, X-ray and optical emissions were fine for spotting tidal disruption events in dust-depleted galaxies. But infrared observations were key in finding star-shredding black holes in dusty galaxies. It's not that they're only occurring in one type of galaxy, as people thought based only on optical and X-ray searches. If you want to understand tidal disruption events as a whole and use them to probe supermassive black hole demographics, you need to look in the infrared band. The findings from the MIT researchers could also explain why tidal disruption events don't seem to radiate as much energy as is predicted by theory, with the team suggesting that the energy deficit is the result of dust-absorbing optical and X-ray emissions, as well as extreme ultraviolet radiation from tidal disruption events. Adding the 18 new tidal disruption events they discovered to previously observed events of this nature, the MIT team estimates that galaxies experience a tidal disruption event roughly once every 50,000 years, which is in line with previous theoretical predictions. As Kara concluded, this gives us confidence that we don't need all this exotic physics to explain what we're seeing, and we have a better handle on the mechanics behind how a star gets ripped apart and gobbled up by a black hole. We're understanding these systems better. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.
So we don't know where the laws of nature came from. We don't know why the universe began in the way that it did, if indeed it had a beginning.
One of the biggest questions, perhaps the biggest question of all, that we can ask about our universe is where, if we go all the way back, it came from. Before the stars and galaxies, before the emergence of atoms, before the very first moment of time ever passed and elapsed, how did it all begin? What existed before the Big Bang? Why did the Big Bang happen? What caused the Big Bang? It's a question that many of us wonder about, and a question that, despite our best efforts, science still doesn't have a convincing, compelling answer for that's supported by actual measurable data.
So the picture is that 13.75 billion years ago, the universe began. Why? We don't know. We don't know the answer to questions such as what happened before the Big Bang.
Regardless, it never hurts to ask the biggest questions of all and take stock of where we are at present. But first, we have to accept that this is a question where science and religion are profoundly enmeshed, if not in practice, at least historically. After all, most religious traditions, past and present, have a narrative that tells of the origins of all things, a myth of creation. These narratives are sacred, as they describe the origin of all things through the action of a deity or deities, or through some process that defies the workings of nature. To deal with the very tough question of the first cause, creation myths make use of an absolute being, a cause that lies outside the normal workings of the world, outside space and time, outside the chain of causation that defines our material existence. It makes sense. In pre-scientific times, how else would one account for the existence of the world? To boot, creation myths serve a social purpose, establishing the power hierarchy that holds the tribal morals together, the value system that defines their shared creed. When God first appears in Genesis 1, it is clear to the reader that He is the Creator, omniscient and omnipresent, not of this world, but somehow in this world, a pervasive, immanent presence that makes itself felt in mysterious ways.
The universe is 13.8 billion years old. We measured it, so it's just stop it. But that doesn't mean you can't be spiritual and you can't be religious, I would say, and it doesn't mean you can't believe in God or gods or...
Different religious cultures would have different narratives of creation, most of them with supernatural gods responsible for the creative act, marking the beginning of time itself. Such narratives make use of a linear time, with a beginning at some point in the past. Some traditions, for example, the Maoris of New Zealand, suggest that the world came to be on its own, without the influence of an active deity. It appeared out of nothing, from an ineffable urge to exist. Others, notably from China and India, would report that in the beginning there was an egg floating in nothingness, and that the egg cracked the world, and its forms came to be from the different parts of the egg. Yet in other creation narratives, as in a Taoist myth from before 200 BCE, the cosmos emerges on its own, as order coalesces from its dynamic interplay with chaos. The Hindu myth of the dancing Shiva uses the god's choreography to illustrate cycles of creation and destruction as the cosmos emerges and collapses endlessly in the infinity of time. And the Jains, also of India, do away with creation altogether, suggesting that time has no beginning or end. These cyclic time or no-time narratives complete the 5 archetypes of creation. In scientific times, the question of the origin of all things has returned full force, under research in modern cosmology. Most of the mathematical formalism to deal with this question was developed during the 20th century, with Einstein's theory of general relativity. The central idea is that matter tells space how to bend, and thus, if we know or can effectively model the matter that exists in space, we can solve the equations for its geometry and, potentially, for the origin and fate of the cosmos itself. To dive into this question and truly do it justice, we're going to have to separate out 3 commonly confused and conflated things, and then talk about all 3. The hot Big Bang as it applies to our universe, the theory of cosmic or cosmological inflation, and how it precedes and sets up the Big Bang. And then the question of an ultimate beginning or origin to our universe, and how both inflation and the original idea of the Big Bang are dissatisfying for providing such an answer. In the early 20th century, 4 important pieces of information, 1 theoretical and 3 observational, came together in an absolutely revolutionary way. They were as follows. On the theoretical front, Alexander Friedmann had shown, within the context of Einstein's general relativity, that a universe uniformly filled with any form of matter and energy cannot be static and stable, but must expand or contract, with the rate of expansion-contraction determined by the overall energy density of space. Observationally, Henrietta Leavitt established a relation between the period of brightening and faintening Cepheid variable stars and their intrinsic brightness, the period luminosity relation. Observationally, Vesto Slipher measured the amount that light is shifted, red-shifted, or blue-shifted from our frame of reference within the solar system of spiral and elliptical nebulae, before we even knew they were galaxies, and determined that they must be receding from us at incredibly large speeds. up to thousands of kilometers. And then observationally, Edwin Hubble, and with him, Milton Humason, began identifying variable stars, the same types of variable stars that Henrietta Leavitt had identified a period luminosity relationship between in those spiral and elliptical nebula, allowing us to measure their distances and confirming their extragalactic nature. These four pieces of information, when put together, led to the idea of the expanding universe. So if the universe is expanding, what does that imply? Going forward in time, it means that as space itself expands, the matter within the universe dilutes to lower densities, because matter is made of a fixed number of particles, but as space expands, the volume it occupies continues to increase. Hence, the universe gets less dense over time. For radiation, like photons or light waves, not only does it dilute to lower densities, but because the energy of a light wave, or a photon, is determined by its wavelength, then as the fabric of space itself stretches to greater distances, the energy of each light wave stretches as well, causing the universe to not only expand and dilute, but to cool as well. However, that means if we consider what happens to the matter and radiation in the universe if we run the clock in the other direction, backward in time, we find that precisely the opposite conditions would have occurred. The universe, when it was younger, would have been both denser and hotter. Go farther back in time, and all the matter and radiation would have occupied a smaller volume, making the universe denser. The light that was stretched by cosmic expansion, if you run the clock backward, would have had its wavelength shortened in the past, leading to hotter conditions and higher temperatures. And if you imagine going all the way back, as far as the laws of physics will let you, you'll arrive at a singular state, where all of the matter and radiation were contained within a single point of infinite density and temperature. This was the original notion of the Big Bang, and working out the physical details of how matter and energy should interact in this early, hot, dense environment led to 5 cornerstone predictions of the theory. First, the universe should be expanding, displaying an unambiguous redshift distance relation among extragalactic objects. Second, the universe should have begun somewhat uniform, and cosmic structures like stars, galaxies, groups, clusters of galaxies, and a large-scale cosmic web should form and grow progressively over time. Third, the universe was hotter in the distant past, hot enough at one point that neutral atoms couldn't stably form, leading to the prediction of a relic, low-temperature, omnidirectional black-body spectrum having radiation background, the cosmic microwave background, today. Fourth, the universe was once so hot in the distant past that even atomic nuclei couldn't stably form, leading to the prediction of relative abundances of light elements. Hydrogen, helium, lithium, and their various isotopes all formed in the crucible of the early universe. And last, the universe should have once been so hot that neutrinos played an important cosmic role, leading to a fifth prediction that has only recently been confirmed, that these cosmic neutrinos should leave detectable imprints in both the large-scale structure and the leftover radiation from the Big Bang. With strong observational support for all 5 predictions, the Big Bang reigns unchallenged as our leading theory of the early universe, as it has been since the mid-1960s, when the cosmic microwave background was first discovered. But even as evidence was accumulating for the hot Big Bang in the 1960s and 1970s, puzzles emerged as well, things that were observed but that the Big Bang itself couldn't explain. For example, if the universe began from a singular state of arbitrarily high temperatures and densities, then there are at least 3 observations that simply don't make sense. First, the horizon problem. If we look in different directions, we see the universe as having the same temperature and density everywhere. But even since the start of the hot Big Bang, these regions never had time to communicate, exchange information, or reach thermal equilibrium with one another. So how did they evolve to reach the same temperature and conditions everywhere? Second, the flatness problem. In an expanding universe in general, there's a fight between the initial expansion rate that drives things apart and the gravitational effects that work to bring everything back together. In our universe, we observe that these two opposing forces are pretty much perfectly exactly balanced, leading to an exactly spatially flat universe. So why was our universe born with those properties? And third, the monopole, or ancient relic problem. If the universe reached these arbitrarily high temperature and energy conditions, then why are there no exotic, leftover heavy relics, right-handed neutrinos, magnetic monopolies, and other particles that should be observable and left over today? We can always shrug our shoulders and mutter something like, "Those must have just been the initial conditions or the way the universe was born." But that runs counter to the enterprise of science. Instead, we look for a mechanism that would mandate and set up these conditions. That mechanism sprung forth in 1980 in a remarkable paper by Alan Guth, who noted explicitly that an early, rapid, and relentless phase of exponential expansion, where the universe's energy was not distributed among matter and radiation quanta, but rather was inherent to the fabric of space itself, either in a field or via some other mechanism, would solve all three of these problems. The reason the universe had the same temperature and density everywhere comes about because in the past, things were causally connected. They were stretched to be far apart by this early expansion phase. The reason the universe appears flat today is because regardless of how it started off, inflation stretched things so that the part that's visible to us appears indistinguishable from flat. And the reason there are no ancient leftover relics is because the universe never reached arbitrarily high energies or temperatures, just the maximum temperature that was achieved in the aftermath of the end of inflation. By providing a mechanism by which these three observables could be explained, inflation presented a powerful alternative to the standard hot Big Bang. Once additional problems were solved, to show how an isotropic, homogeneous, early universe could be recovered at the end of inflation, something else became remarkably clear. That inflation would provide a quantum mechanism for seeding the universe with initial imperfections, or the seeds of cosmic structure, that would later become observable in detail. Inflation would make many testable predictions about the seeds of cosmic structure that should appear in both the cosmic microwave background and also in the large-scale structure of the universe, as well as setting a cutoff for a maximum temperature that ought to be observed far below the Planck scale. These predictions, made in the 1980s, were borne out by observations made from the 1990s to the present, including a spectrum of imperfections, density, and temperature fluctuations that are almost, but not perfectly, scale invariant, density imperfections that are 100% adiabatic and 0% isocurvature in nature, fluctuations on superhorizon scales which are larger than a signal moving at the speed of light in an expanding universe could create, and a finite maximum temperature to the universe during the hot Big Bang, which should be significantly smaller than the Planck scale. Because inflation represents an exponential expansion of space, though, rather than one that terminates in a singularity like the original model for the Big Bang, however, it sets up a very different picture of the beginning, of a whoosh that led to a Big Bang, rather than the emergence of time and space from a singular state. Now, we get to address the really big questions. What does all of this mean for the true beginning of the universe, if such a thing even existed? Back when we were only considering the hot Big Bang, without inflation, we could extrapolate back and reach a singular state, where the size of the universe would go to zero, in a finite amount of time. But because inflation expands space in an exponential fashion, it's impossible to extrapolate it back to a singularity. With exponentials, it would take an infinite amount of time to go back to a state where the universe had zero size. To make matters worse, the observable evidence that we have for inflation, where these quantum fluctuations generated by inflationary processes get imprinted on our visible universe in ways we can measure and detect, is confined to only about the final 100 or so doublings of the universe before inflation ends. This is monstrously insufficient for what we want to know, as this corresponds only to a time period of about the final 10 to the power of negative 32 seconds before inflation ends and gives rise to what we know as the hot Big Bang. If we were hoping that we could just push off a singular beginning to an earlier epoch, inflation squashes that hope. There is nothing we can observe that tells us anything about what, if anything, gave rise to inflation. One aspect of inflation that's fascinating is known as eternal inflation. If you look at the details of how inflation works, pretty much any model of inflation that you can construct that actually works, that gives you enough inflation to solve those three problems with the original Big Bang and produces the quantum effects necessary to seed the universe with the imperfections that lead to our large-scale cosmic structure, will cause your universe to expand in such a way that while inflation ends in some regions of space, like our own, leading to a hot Big Bang, there will be infinitely more. In other words, once inflation begins, it not only wipes out any information of what existed before, but the inflationary state will persist eternally into the future, sporadically, due to the same quantum fluctuations that seed the structure of the universe. There will be individual regions where inflation does end, and a hot Big Bang ensues. But they will be spectacularly outnumbered by regions where inflation never ends. In fact, no two independent regions where Big Bangs occur will ever overlap, as the inflating universe drives them apart. However, as tempting as it is, even eternal inflation has its limits. It's only eternal to the future, not to the past. In fact, it can be, and has been, proven that inflationary spacetimes are not past time-like complete and must have emerged from some prior, non-inflationary, and possibly singular, state itself. You can't weasel your way out of this past time-like incompleteness by appealing to alternatives to inflation either, such as bouncing cosmologies or cyclic cosmologies, as those have been shown to suffer from the same problems. But that, alone, isn't enough to tell us that the universe must have begun from a singularity either. It may have begun from a singularity, but that's not a necessity. For example, you can also easily design a past time-like complete spacetime where inflation occurs just by modeling the scale factor of your universe, whose change over time determines the expansion rate, as a growing exponential plus a constant, rather than a pure, growing exponential on its own. All of which is to say, the hot Big Bang may be the best description we have of our early universe, but it wasn't the very beginning, as there's a cutoff in how far back you can extrapolate the temperature and density of our matter and radiation-rich universe. Before the hot Big Bang, there was a period of cosmic inflation, which set up and gave rise to the hot Big Bang, where space was full of energy, not matter and radiation, and expanded relentlessly and in an exponential fashion. But inflation couldn't have gone on forever, and must have arisen from some pre-existing, non-inflationary state that we can, unfortunately, say very little about, except for the large number of things that we can firmly state it couldn't have been. After all, scientific narratives of creation remain unable to make sense of the first cause. This is due to the very nature of science, which calls for a conceptual framework to set the stage for models to exist. Before we talk about bounce models or quantum fluctuations, we need to describe space, time, energy, matter, what laws hold them together, and how we can apply them within the concept of time. To say that we have solved the question of the first cause, using either an oversimplified model of quantum cosmology or a highly hypothetical one that makes use of extra spatial dimensions or separations between our physical dimensions and others, is not just confusing to many, but incorrect. Despite remarkable progress in our understanding of the physical universe and its 13.8 billion-year-old history, when it comes to why is there something rather than nothing, we remain stuck. Now, you can choose religious faith as an answer, or you can choose to believe science will conquer it all. But you can also, like the Greek skeptic Pyrrho, embrace the limits of our reach into the unknowable with humility, celebrating what we have accomplished and will surely keep on accomplishing, without the need to know all and understand all. It's okay to be left wondering. Curiosity without mystery is blind, and mystery without curiosity is lame. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see